if I set up a coordinate system here, if I have a point in space here, that would be a distance r away. If I project it down onto the, put a projection onto the xy plane, this angle right here would be theta, and then this angle here is phi. So yeah. There are sometimes some books that will switch the letters phi and theta, which is really inconvenient. So what they figured out is that there's an independence between the radial portion and the angular portion of it. And so they say, well, let's just let psi, which depends upon r, theta, and phi, to be some function of r times some function of theta and phi. If that is the case, when we're doing partial derivatives here, I know psi as the y piece right there, since I have r, y does not depend upon r at all, and so what I'm left with down here is I have 1 over r squared, del r squared, del r, plus 1 over r squared sine theta. Del theta. Del y, del theta. I lost something there. I lost my sine theta. Since the r piece of it has no dependence upon theta, that's why it suddenly has gone away. Plus 1 over r squared sine squared theta. Del squared y over del phi squared. Plus, and just to keep in track with the notes over there, 2m of not m, it should be mu over h bar squared times z e squared over 4 pi epsilon sub naught r plus v plus e equals 0. Oh, let's be there. Plus e times ry. Y doesn't depend upon r. I was right about that, but that doesn't mean it just goes away. It acts as a constant. And r doesn't go away, it just acts as a constant. My portion over here, so I need to somehow get rid of that. So what I'm going to do is I'm going to multiply everything by little r squared over ry, just to get it into the right form. R squared is going to cancel out. I'm going to be left with 1 over big R, del R squared, del little r. Plus, over here, my r squared is going to cancel out. My r is going to cancel out, so I'm left with 1 over y, del theta, sine theta, del y, del theta. Plus, well, the r is going to cancel out again, and the big R and the little r squared is going to cancel out, so I'm left with 1 over y sine squared theta, del squared y, del phi squared, plus ry is going to cancel out, and I end up with an r squared there, so I get 2 mu, that's a 2, h bar squared, r squared, z e squared over 4 pi epsilon sub naught r plus e equals 0. Now we have each of these terms has either theta and phi in it, or it has r in it. So by doing the separation of variables and the other manipulation we did, we reduced it down to an equation where I can just look at the r piece of it. That is dependent upon r, and that is dependent upon r. And I can look at the piece that doesn't have that in there. So if I go ahead and say that, just want to make sure that no, it's not a mistake. I just feel like I lost a variable in there somewhere. Oh, okay. Sorry. Now, the radial piece and the angular piece, neither of them are equal to 0. They're equal to something. So what I'm going to do is I'm going to set my radial piece equal to A, and the angular piece I'm going to set equal to what have to be the opposite, negative A. So I've broken this down into 2 sets of equations now. Well, let's concentrate on the radial part first. So I have 1 over r, del r, r squared, del r, del little r, plus 2 mu r squared over h bar squared, z e squared over 4 pi epsilon sub naught r plus e is equal to a. It's equal to something. Multiply everything by r, and I have del r squared, del r over del little r plus 2 mu r squared h bar squared r. Let's go ahead and distribute z e squared over 4 pi epsilon sub naught little r plus 2 mu little r squared h bar squared r e equals r. So much cleaner now. Actually, it is so much simpler at this point. It is now just a matter of solving. And therefore, take it the other one. 1 over y delta theta sine theta del y del theta plus 1 over y sine. That's supposed to be a y, not a sine. Y at this point, we can do separation of variables again. We've gotten rid of r, we have an equation with just thetas and phi's in it. If you make the assumption that there's an independence between theta and phi, then that should be a y there. Then y, we can say, is equal to some function of theta times some function of phi. We go through the process again, and we ultimately end up, well, a new separation constant. So this time I'll use b. We end up with 1 over phi d squared phi d phi squared plus b equals 0. And we will have the other equation from the sines. So we have sine of theta over theta d theta sine theta d phi d theta, run out of room here, plus a sine squared theta minus b equals 0. So we now have 3 equations. This equation right here has only r in it as my variable. This has theta in it as a variable, and this has phi in it as a variable. So this is the general technique, and at this point it's just a question of how do you actually solve these pieces. So you just need to find some equation that works for this. And the equation that works for phi is some constant e to the I m phi plus c sub 2 e to the negative I m phi, where b is equal to m squared. That's a phi, not a b there, that's a phi. And so ultimately it breaks down to one of those terms is going to go away. And more importantly, we have a value for b, which we can then plug into my other equation right there. Yeah, I started on this and I thought, okay, this is simple enough, but it really is a pain. Okay, so I'm going to put a stake in its heart. And then a miracle occurs. Ultimately, what you end up with is something that really can't be solved analytically particularly nicely. You end up with what are called Legendre polynomials. Associated Legendre type differential equations. And the only reason that we have a way of solving them now is because some guy named Legendre, or someone associated with him, that's what he did. There's a whole bunch of 18th and 19th century mathematicians who all they did was try to solve these equations that are not particularly easy to solve. And so we exploit that and come up with a group of solutions that have multiple answers, which is vague. But in essence, the solution to this equation uses Legendre polynomial. I'm going to write down this coefficient because it is just something to behold. Here's the solution for that theta equation. It's an L. Got lost. There we go. There we go. Obviously, we've got these vague terms in here. We've got N, M, and L. Those are three of the quantum numbers right there. It's solutions to basically Schrodinger's equation. But because there are multiple solutions, well, the multiple solutions are the quantum numbers. A, big A, is equal to L times L plus 1. L is considered the angular momentum quantum number. M, I don't have written down, so it's buried in the text somewhere. And, yeah, there it is. So N is the shell, L is the and then the fourth quantum number is beyond the scope of this one. I was going to add more, but I'm not quite sure it really satisfies much. So psi equals Legendre polynomial, radial function, and the azimuthal, or is that the other one? And the phi bit. And now you can go home and share your adventures. They will be everyone will be enthralled. That is it. So, yep, it's a lot. Any questions? I assume it's really obvious that I could have skipped up most of the steps. Just wanted you to get a flavor for it. And if you don't get sarcasm, it's not obvious. At least to me. I've met some people though that it might be obvious to them.